All right, continuing on in techniques of integration, we're going to learn one of the more powerful techniques of integration. It's called integration by parts. Integration by parts, it's going to be kind of sort of like a product rule. And let's get started with it. As I just said, it's pretty powerful. Integration by parts is a pretty powerful technique of integration. You're going to see it on and off throughout the calculus sequence, and it's going to be something that you will definitely see used quite a bit in a differential equations course. It's kind of, sort of like a product rule, but integration by parts will require a double substitution. So let me kind of just show you where the integration by parts formula comes from. So we're going to kind of derive the integration by parts formula. So I'd start off in my seeing where it comes from by saying, let's suppose u and v are functions of x. They're two differentiable functions of x. That means we can differentiate them. And in fact, we can differentiate their product using the product rule. So when we differentiate with respect to x, u and v, so when we ddx u times v, the product rule gives us the derivative of the first times the second plus the first times the derivative of the second, or u prime v plus u v prime. And I'm just going to rewrite that now. I'm just going to rewrite it as uv prime plus u prime v. Just use the commutative property of addition. So all we've done is use the old product rule of derivatives at this point in time. Now I can write this, instead of using the prime notation, I can use the Leibniz notation. So I can rewrite the derivative of u times v as u dv dx plus v du dx. So instead of v prime, I have dv dx, and instead of u prime, I have du dx. Now if I go one more step and bring back a really old topic from Calculus 1, differentials. So in terms of just differentials only, I can rewrite that as d of u times v equals u dv plus v du. So that's just writing it in terms of differentials. Let me write that down again. I can solve that equation. I can solve it for u dv. I mean, it's an equation, so if I solve it for u dv, I'm going to subtract v du from both sides of that equation to get u dv equals d of u times v minus v du. Folks, we know integration and differentiation are inverse operations. That is, they undo each other. Integration will undo differentiation. So what I'm going to do now is I'm going to integrate both sides of that equation. So I'm going to integrate the left side and I'm going to integrate the right side. And notice when I'm integrating the right side, I'm making use of a property of indefinite integrals. And we'll see that integral of du times v, we're doing the integral of a derivative. They're inverse operations. They undo each other, which is why we just end up with u times v there. So we end up with the integral of u dv equals u times v minus the integral of v du. That last line there, folks, that is the integration by parts formula, and we just derived it. So let me write it down as a theorem. If u and v are functions of x and they have continuous derivatives, then the integral of u dv equals u times v minus the integral of v du. And actually, I guess the derivation that we just went through, some people would call it the proof to this theorem. But yeah, look, we just kind of came up with it. So let's see how integration by parts works. Let's evaluate the integral of x e to the x dx. Folks, this is a classic example for integration by parts. In any calculus book you pick up and you look at the section on integration by parts, if this isn't the first example you see for integration by parts, it would definitely be the second example. So let's head off to the chalkboard and crank this through integration by parts to see the mechanics of using integration by parts. All right, this integration technique, integration by parts, it's a pretty powerful technique. It's a technique you will see in a future differential equations course, as well as, it's fair game the rest of your time in the calculus sequence. This first example is what I call a classic example. It doesn't matter what calculus book you look at, this example is either the first or second example of integration by parts. So I'm going to run through the example and then I'm sure we'll come back and do more examples. But here's how this one goes. Integration by parts is kind of like a double substitution. You have to figure out, when you look at the original problem, what you're going to let u equal and what you're going to let dv equal. Well, here, I'd let u equal x, then dv is e to the x dx. You have to account for every piece in here. So let me block it off. That is u, and all of that was dv. Once you write down what u is and what dv is, you then have to compute du. Well, du is the derivative, so du is dx. And you have to compute v. So there's like a little mini integration problem within this integration by parts. If dv is e to the x dx, v, it's the antiderivative of e to the x dx, which we know the antiderivative of e to the x is e to the x. And then a habit I got into many years ago, and it's one I strongly encourage you to get into, as you will see by our last example for this section, is, I got in the habit of writing down the original problem, equals, and now I put the result of cranking it through the integration by parts formula. So the integration by parts formula is u times v minus the integral of v du. And now it's just one step, one more step. The antiderivative of e to the x is e to the x. Tack on the plus c. That's it. So let's head back to the slides, see what's coming up next. All right, so we did that example, and as I mentioned, it's a classic example. Cranked you through the mechanics of integration by parts, and we saw that it really is a double substitution. You're looking at the original problem, and you're figuring out what is u and what is dv. That example is a classic example because it actually hits both parts of the following guidelines. So these are the guidelines that I would give for integration by parts. Two parts here. Number one, I suggest try letting u be the portion of the integrand whose derivative is a simpler function than u. Then dv will be the rest. Guideline 2. You could try letting dv be the most complicated portion of the integrand that is easily integrated. Then u will be the rest. And notice how that first example, why it's a classic, it does fit part 1, it does fit part 2. One very important note, dv should have the dx from the original integral with it. So whatever you're saying dv is, dv will equal, whatever, dx. It's going to have the dx with it. You have to account for all pieces of the original problem. So I think it's time to look at another example. Let's integrate x cosine x dx. So get this written down because, I'm heading off to the chalkboard to do it. All right, this example, evaluate the integral x cosine x dx. Another example of using integration by parts. And we just looked at some general guidelines, tips if you will, for what to let u equal or what to let u equal or what to let dv equal. So when I consider those guidelines and I look at this problem, I would say, you know what? If I let u equal x, then dv will be cosine x dx. The derivative here is a simpler function. Likewise, dv being cosine x dx, that's the most complicated part that I can easily or quickly integrate. And the antiderivative of sine, or the antiderivative of cosine, is sine. So, I write down the original integral. I crank it through integration by parts. U times v minus the integral of v du. And to finish it off, the antiderivative of sine. Antiderivative of sine is negative cosine. So I'd have minus a negative. I'll make that plus. And that's all there is to it. So you need to practice one now. Go to the exercises, pause the video, do number 9, and after you do number 9, restart the video. I'll be here at the board working through it. Okay, number 9, you were asked to integrate x cosine 5x dx. Classic integration by parts. I'd let u equal x, dv is cosine 5x dx, du is dx, and v is 1/5 sine 5x. So I write down the original integral, crank it through integration by parts, u times v, so I'll write that as a 1/5 x sine 5x, minus the integral of v du. Well, when I put the v in here, I'll rip the 1/5 out front. And now to finish it off, the antiderivative of sine 5x is negative 1/5 cosine 5x. So you know what, I'd probably put one more step in here. I would have it as 1/5 x sine 5x plus 1/25 cosine 5x plus c. That's it for number 9. Hopefully that's what you came up with. So let's head back to the slides, see what's next. All right, so as we saw in that example, hopefully you're starting to see the mechanics of how to utilize integration by parts, and hopefully you were able to get number 9. Next up is we're going to do an example that has 4 parts. We're going to evaluate in part A the integral of natural log x dx. Part B, we're going to integrate x squared natural log x dx. Part C, we're going to integrate from 0 to 1 inverse sine x dx. And then in part D, we're going to integrate x squared sine x dx. So you know the drill. Get all 4 parts written down because I'm going to be heading off to the chalkboard to work through them. All right, this example had 4 parts, 4 different integrals to evaluate, and I wrote them over on this side of the board. In part A, integrate natural log x dx. Part B, integrate x squared natural log x dx. Part C was the definite integral from 0 to 1 inverse sine x dx. And then part D, x squared sine x dx. So let's go over here and I'll write down part A. Folks, you really only have one choice here for what u is and what dv is. The only choice you have is to let u equal ln x and dv is dx. There's no way you would let dv equal ln x dx because you don't know what the antiderivative of ln x is. That's what we're going to come up with here. So if u is ln x, du is 1 over x dx. If dv is dx, then v is x. So write down the original integral. Crank it through integration by parts. U times v minus the integral of v du. Well, this one isn't too bad now. Look at it. That second integral, x times 1 over x, that's just 1. So the antiderivative of 1 dx is just x. And check it out, folks. Up until right now, you knew the derivative of natural log x. But you didn't know what the antiderivative of natural log x is. Now you know. Now you know that the antiderivative of ln x dx is x ln x minus x plus c. So that's like a formula that you now know. Let's do part B. Actually, I want you to do part B. So I want you to pause the video, do B. After you've done it, restart the video, and hopefully you'll have it correct. Alright, so here we're asked to integrate x squared natural log x dx. And I'm thinking of my guidelines. When I think of my guidelines, you know, I'm going to let u equal natural log x and dv equal x squared dx. So if you're thinking, is that legal? I thought the first thing that we saw had to be u. No, it's the whole thing together. So I'm making this u. And the x squared dx, that's dv. Doesn't have to go in order. What you see first is u and then the rest is dv. Let's continue on. Hopefully you did this. You got du is 1 over x dx. V is a 1/3 x cubed. So I write down the original integral. Crank it through integration by parts. U times v. So it's a 1/3 ln x cubed. You know what? I don't like to write it like that. I don't like my x's together like that, so I'm going to write the u times v as 1/3 x cubed ln x. I like the way that looks better. Minus the integral of v du. Well, I'll take the 1/3 and rip it out front. So 1/3. So I'd have, what, x cubed times 1 over x dx. And well, x cubed times 1 over x, that would simplify to just x squared. So I get a 1/3 x cubed ln x minus 1/3 times a 1/3 x cubed. Or I would probably have my final answer as, you know, minus 1/9. Okay, that's it for part B. Hopefully you got it correct. Actually, I want you to also now pause the video and do part C. Pause the video, do part C, and after you've done part C, restart the video, And I'll be here at the board working through it to make sure you got it correct. All right, part C, you were asked to attack the definite integral from 0 to 1, inverse sine x dx. Another classic integration by parts. And I really only have one way to start this and trying to figure it out. And it's by letting u equal inverse sine x, then dv is dx. We know the derivative of inverse sine is 1 over the square root of 1 minus x squared dx. And here the antiderivative, you get v is equal to x. So I'm going to crank this through integration by parts. I'm going to leave off the limits of integration for this next step. I'll bring them back at the very end, but I'm leaving off the limits of integration. So we have the integral, inverse sine, crank it through integration by parts, u times v. So that's x inverse sine x minus the integral of v du. Well, that gives me x over the square root 1 minus x squared dx. How am I going to take care of this integral? That's right, good old-fashioned u substitution. You let u equal 1 minus x squared. du is a negative 2x dx. So when I crank this through, I'll put it in square brackets, my u substitution, I'm going to get, you know what? I'm going to have to put a negative 1/2 du in for the x dx. So the negative 1/2 will come out in front of the integral side. So there's my du. So I'll have a 1 over the square root of u. Well, 1 over square root u, that's u to the negative 1/2. So I keep going. No, I'm going to get a plus here. That's kind of nice. U to the negative 1/2. Get an antiderivative. That's u to the 1/2 with a 2 right there. Resubstitute. So I get x. I left off my inverse sine. X inverse sine x plus u to the 1/2. U is 1 minus x squared. And now I bring back the limits of integration. I told you I would at the very end. So there's bringing back the limits of integration. And let me pull it up here to evaluate. So let's see, put 1 in for the x first. So you have 1 times inverse sine of 1. Well, inverse sine of 1 is pi over 2. Plus 1 comes in here for x, so this gives me 0, square root of 0, 0. Minus, now the 0 comes in. Well, that gives me 0. This is 0. This is square root of 1. Square root of 1 is 1. Well, that's it. So a lot going on in this example, which I thought was kind of cool. You had to use integration by parts, and integration by parts got us to right here. And then after integration by parts, this integral had to be handled by a u substitution, which is kind of cool. And then when we did the evaluation, we had to remember the basics of the unit circle. So that was it for part C. Hopefully, that was part C. Hopefully you got part C correct. The only one that's left is part D. So let's do that together. But first let me erase the board. I'll be right back and we'll do part D together. Okay, part D, we're asked to integrate x squared sine x dx. So here I go. Start off. I'm letting u equal x squared. dv is sine x dx. du is a 2x dx. V is negative cosine x. So when I crank this through, I write down the original integral. I crank it through integration by parts. I get u times v, so that's a negative x squared cosine x, minus the integral of v du. Okay, so when v du comes in here, I'd have a negative cosine x times 2x dx. I'm going to take that negative 2 and rip it out front of this integral. So that makes it a plus 2 x cosine x dx. So, how do we attack this integral? Integration by parts. So this is an example where we have to do integration by parts more than one time. The first crank through of integration by parts gives us this. Now we use integration by parts on this integral. U is x, dv is cosine x dx, du is dx, v is sine x. So I'm cranking just that integral through integration by parts. So I need to remember to bring this down. And I'm going to put the result of the second integration by parts inside square brackets. So it's u times v minus the integral v du. And now it doesn't take much for us to finish this off. You know what, I'm going to distribute the 2. So I have a 2x sine x. Antiderivative of sine is negative cosine. So we'd have minus a negative, that's plus. So there, we had to use integration by parts 2 times. Just take your time with it. Neatness and keeping things organized can matter quite a bit here. So let's head back to the slides and see what is next. All right, in that example, we saw in part A, the antiderivative of ln x, we ended up coming up with a nice little formula for that. I hope you were able to do B and C, and then, part D. So we're starting to see we've done a lot of examples so far of doing integration by parts. Hopefully you're starting to get some comfort and familiarity with it. Let's do another example. Let's integrate e to the x sine x dx. So you know the drill. Get this written in your notes because I'm heading off to the chalkboard to do it. All right, this example, we're going to see why I stress writing things down the way I write them down. We're asked to integrate e to the x sine x dx. So it's kind of a classic start with integration by parts. Let u equal e to the x. dv is sine x dx. du is e to the x dx. v is negative cosine x. So we write down the original integral. I've been stressing this every example. Crank it through integration by parts. U times v. So that's a negative e to the x cosine x. Minus the integral of v du. Well, I'd rip the negative out to get plus e to the x cosine x dx. Yep, got to crank that through integration by parts. So we're doing integration by parts again. So we get a u is e to the x, dv is cosine x dx, du is e to the x dx, and v is sine x dx. All right, so let's see, I got to bring this down. Plus, I'm cranking this integral through integration by parts, so I'll put it, the result of integration by parts in square brackets. So we have a u times v, so e to the x sine x. Oops, sorry there. I got a little carried away with my dx's. Minus the integral of v du. And right now you're saying, we're at an integral, we're right back to where we started. So it's like we're on a vicious circle, or something's not going to work out here. And this is why I've been saying, continue to write down the original integral and the result of integration by parts, because if I clean this up a little, and by clean it up, it's just rewriting this as, you know, e to the x sine x, and then, you know, just minus this integral. This original integral is equal to this. Folks, this is an equation. That's why I've been stressing to write it down every single time. Because our goal is to come up with an antiderivative for e to the x sine x dx. This is an equation. Treat it like an equation. I can add the integral of e to the x sine x dx to both sides of this equation. And if I do that, that would give me 2 integral e to the x sine x dx equals negative e to the x cosine x plus e to the x sine x. So to get an answer for this, I just have to now divide both sides of this equation by 2, and boy, I have to pull it up here now. So I get the antiderivative of e to the x sine x dx equals negative 1/2 e to the x cosine x. Divide by 2 plus 1/2 e to the x sine x. Oh, and then I have to remember the plus c. That's kind of cool. So, you know what I'd like you to do right now? Practice by doing number 29. So you know the drill. Pause the video, go to the exercises, do number 29. When you're done, restart the video. I'll be here at the board working through it. All right, number 29, you were asked to integrate e to the negative x sine 4x dx. Hopefully you started off by letting u equal e to the negative x dv sine 4x dx, du negative e to the negative x dx, and v is negative 1/4 cosine 4x. So then when you crank this through integration by parts, remember to write down the original. Equals, now the result of integration by parts, u times v, I'll write that as negative 1/4 e to the negative x cosine 4x, minus the integral of v du. Well, negative times negative is positive, but I will rip the 1/4 out front. And yep, we got to go through integration by parts again. This integral here requires integration by parts. So u is e to the negative x dv cosine 4x dx, du negative e to the negative x dx, and v is 1/4 sine 4x. So we're cranking that second integral here. We're cranking that through integration by parts. So let me pull this down. Negative 1/4 e to the negative x cosine 4x minus 1/4. Okay, I'm going to put the result of integration by parts inside square brackets. So I have a u times v. That's a 1/4 e to the negative x sine 4x minus the integral, okay, v du. So when I put v du in there, I'm going to have a negative 1/4 that I can rip out front of this integral. So 1/4 e to the negative x sine 4x dx. And yes, I'm right back to an integral that I started off with. So here's what I would do. Just a little bit of cleanup. Let's distribute this negative 1/4 on through, so I get a minus 1/16 e to the negative x sine 4x minus 1/16 the integral e to the negative x sine 4x dx. Keep in mind that's what, all of that mess, that's what this integral is. It's an equation. So add 1/16 integral e to the negative x sine 4x dx to both sides of the equation. So you get a 17/16 the integral e to the negative x sine 4x dx equals negative 1/4 e to the negative x cosine 4x minus 1/16 e to the negative x sine 4x, and then multiply both sides by 16/7 to get this as your answer, e to the negative x sine 4x dx equals, all right, so you go ahead and multiply this by 16/7. That gives you what? Negative 16/17. That gives you negative 4. Oh, fun with fractions. Negative 4/17 e to the negative x cosine 4x. When this gets multiplied by 16/17, that's a 1/17. E to the negative x sine 4x. Oh, and then I better remember at the end to tack on the plus c. Ugly fractions. That's all there was to 29. Let's head back to the slides and see what we're going to end this section with. All right, that last example, and then I asked you to do number 29. It really drove home the fact of why I write things down the way I do. You know, that when I'm using integration by parts, I like to write down the original integral equals the result of what integration by parts would give me, because sometimes you cycle back and you have to do a little algebra, as we saw in that example in number 29 at the very end, to answer the original problem. So, well, you got another example here. We're going to consider the integral sine x cosine x dx. And we're going to evaluate this. In part A, we're going to do u substitution. We'll let u equal sine x. Part B, we're going to evaluate it using u substitution, but this time we'll let u equal cosine x. Part C, we're going to evaluate it using integration by parts. Part D, we're going to evaluate it by using that double angle identity for sine 2x. And then, well, part E, I'm going to say, hey, let's look at numbers 10 and 21 in your book. So get all these parts written down, because I'm heading off to the chalkboard to work through it. All right, this example had 5 parts to it. Hopefully you wrote down all the parts. I'm not putting them all up the board here because I want to do them one after the other. This is integrating sine x cosine x dx, and this is to drive home the fact about recognition. Integration, a lot of it revolves on recognition, being creative, and there's sometimes many ways to do it because they're like little puzzles. So in part A I said let's evaluate this integral, and I told you use u substitution. Let u equal sine x. Well, if u is sine x, you'd have du as cosine x dx. So you'd substitute in and you just have a u du. The antiderivative of that is 1/2 u squared. So you get 1/2 sine squared x plus c. And that might be the most natural way to do this problem. Part B, I asked you to do u substitution where u is cosine x. So part B, it's the same integral, but you're letting u equal cosine x. Well, if u is cosine x, du is negative sine x dx. So when you substitute in, you'd have a u, but negative du would be the sine x dx. So you get an antiderivative, negative 1/2 u squared, and you get that as an antiderivative. On the surface it looks like we have 2 different antiderivatives. They are the same. So this is another little subtlety about integration. Let's say you did this problem and you did this u substitution. Let's say this is an odd numbered problem. You did this, you ended up with this as an answer. You look in the back of the book, and the back of the book has 1/2 sine squared x plus c. But you have that. If you were like me, you're probably thinking, I did the problem wrong. Let me do it again. And you would not have done the problem incorrectly. Can you get this answer to match what's in the back of the book? And I think we can, because we know cosine squared plus sine squared is equal to 1. So that means cosine squared is 1 minus sine squared. So if I substitute in for the cosine squared x, a 1 minus sine squared, distribute the 1/2, and then realize this is a constant and that's a constant. So negative 1/2 plus c. A constant plus a constant is just a constant. You can get that answer to match what would be in the back of the book. Okay, part C. So let me erase this. Part C, I said evaluate that original integral by using integration by parts. Well, integration by parts, I'd look at it and I'd say, all right, I'll let u equal sine x, dv is cosine x dx, du is cosine x dx, and v is sine x. So I crank it through integration by parts. So we get a u times v, well, sine times sine, that's sine squared, minus the integral of v du. And it's like, well, hey, that's the same integral I started with. So I add that to both sides of the equation. Divide both sides by 2. to tack on the plus c. Okay, I still think the most natural way to do this problem was what we did in part A, letting just a basic u sub. And I'm just showing you there are many ways to do this problem. In fact, in part D, I said evaluate using a double angle identity. So a double angle identity, it's like, well, wait a minute. I specifically said the double angle identity sine 2x equals 2 sine x cosine x. I said, well, wait a minute. This isn't a 2 sine x cosine x. It's just sine x cosine x. This is an equation, folks. You could divide both sides of that equation by 2. To get a 1/2 sine 2x. So you could put, for sine x cosine x is 1/2 sine 2x. You can rip the 1/2 out front. And then the antiderivative of, the antiderivative of sine 2x is negative 1/2 cosine 2x. So you get negative 1/4 cosine 2x plus c as the antiderivative. It's like, well, now this is looking a little different than the other answers we've seen. You should be able to get this to match any of the other answers, like the answer for part A or part B, either one. And that's because cosine 2x, remember there are 3 different double angle identities for cosine 2x. So I think if I use this one, I can get the answer that we had for part A. That if I say, well, cosine 2x is 1 minus 2 sine squared x, and then I distribute the negative 1/4, and then I say constant plus constant is just a constant. You know, I get it to match what we had as an answer for part A. This was part D. So we've looked at doing this integral 4 different ways. We got some different looking antiderivatives, but because of trig identities, they all equal the same thing. The moral of the story: don't assume, if you have an answer that looks different in the back of the book, don't assume that you're wrong. See if you can get your answer to match the back of the book. Legally simplified to get it to match the back of the book. And then part E, I said, let's have a look at numbers 10 and number 21. So here's what that refers to. I believe, hopefully I wrote this down correctly. In 10, you were integrating x sine 2x dx. And in 21, you're integrating x sine x cosine x dx. Well, based upon what we just did, sine x cosine x. Sine x cosine x is 1/2 sine 2x. You can rip the 1/2 out front. So it looks like if you know what 10 is, you know what 21 is. It's just multiplied by 1/2. Or vice versa. If you know what 21 is, you get 10 by multiplying by 2. So that concludes this section. So now you can do all the exercises that are assigned. Take your time, Practice, practice, practice. Thanks for watching.